Hello friends, welcome to my second video on self-balancing robot. As you can see in this video, I have prepared a new chassis for my robot with respect to my previous video. Out here I have made several modifications, like I am using 200 RPM motor with higher torque rating, as you can see here, and I have also changed the motor driver to L29A10 from L29 3D that I was using in my previous video. And other than that, in my program I am using a Kalman filter against complementary filter that I had used in my previous video. So now let us see how this has improved the performance of my robot. Now, in order to build a self-balancing robot, we need to know the angle by which it falls, that is theta, so that we can bring it to its original position. And the instrument that we use in our robot to calculate this angle is NPU 6050. But we cannot calculate it directly with only the help of instrument. We need to do some calculations in our program. Basically, the instrument NPU 6050 calculates raw data like angular velocity, acceleration in various directions such as x direction, y direction and z direction. So there are two ways of calculating theta. First of all, if we know acceleration along x direction and acceleration along z direction, then we can get theta equals to tan inverse of acceleration in x direction by by acceleration along z direction. But in this method, the problem we face is that it has a lot of noise. That is, I mean to say, if the angle by which the robot falls is 5 degree, and if we view that angle in our system, it will not show 5 degree, it will show 5.01, 5.1, 4.9, etc. It will never be a constant value and it will be a fluctuating value with lot of noise. Next, if we know the value of omega, that is angular velocity, we can get the value of theta by integrating omega with respect to time. But even by this method, we cannot calculate the actual value always, because this tries to deviate as it is a relative method. For example, if we calculate theta in this case using omega, it will show the theta with respect to its initial position, but we will never get to know it from the zero position. So in order to get an error-free value of theta, we try to combine method 1 and method 2 in best possible manner, and in my previous video I have shown that we can combine this using what is known as complementary filter by using this equation. But even after this, you will find that when the robot falls from its original position and tries to come back after many to and fro deviations, the value of angle theta will deviate from what it should be. For example, if the robot is in zero position, it goes to 5 degree, comes back, again it goes to 10 degree and comes back. Then once it comes back to original position, the value of theta should be 0, but it will never be 0 because there will always be some error. So in this video, I am using Kalman filter instead of that. But instead of explaining what Kalman filter is, I will be showing how to use it in our program, because we have lots of literature on Kalman filter in our internet and it's very complex with respect to complementary filter. Now let's have a glimpse of our program. So this is the body of our program, and as you see, the first function is gyro. This is the function for calculating the angle. Let us see this function. This is that function. I have already explained how to calculate the angle in my previous video, but in this video I am using Kalman filter to calculate the angle. So this is the line that I am using for calculating the angle using the Kalman video. As you can see, the inputs of this function are acceleration angle, that is angle calculated using
Z acceleration and X acceleration. You can see that in this line. Next input is gyro Y. This is the angular velocity, input for angular velocity, which is defined out here, and the loop time, that is defined in these lines. So how we are able to use this function is because we have added a header file out here, Kalman.h. This is the header file or the main program that is used to compute the angle using Kalman filter, and it contains all the mathematical background and equations for calculating the same. In the next step, we input the angle calculated using Kalman filter as the input to our PID controller. My set point is set as 2.2. This I have tried to obtain manually by trial and error method because the center of gravity of the robot does not actually passes to the axis of the wheels. Next, I compute my output of the PID controller and I feed it to the another function, that is motor controller .move, because I have already mentioned earlier in the video that I am using L298N and not L293D. So for this function we have to define a header file lmotorcontroller.h. This contains the program for moving the motor back, forward, or stopping the robot, and many other functions. But basically I am using this function motor controller.move with function inputs as output and minimum absolute speed. The minimum absolute speed, which I have defined already here, is 35. So this we have to input in order to overcome the static